Okay, very quickly we're going to go over introns and exons again. And we have a DNA that's long that is copied and then excised the introns and make it into the messenger RNA, which ultimately gets transcribed. And in fact, sometimes exon 1 and exon 2 is the mRNA. Sometimes exon 1, exon 3 is the RNA. And so there's a lot of diversity. Now, the definition is that the introns are cut out. In fact, initially, the introns were called nonsense DNA, and the exons were called sense DNA. And as far as I know, that is correct. I got thrown last time by the possibility which John mentioned, and that within Drosophila, it turns out that their sex is determined in a different way, for example, than humans. And I'm still not sure how that fits in. But this is the definition. And in fact, what I want to do
As DNA is transcribed into RNA, it needs to be edited to remove non-coding regions or introns shown in green. This editing process is called splicing, which involves removing the introns, leaving only the yellow protein coding regions called exons. RNA splicing begins with assembly of helper proteins at the intron-exon borders. These splicing factors act as beacons to guide small nuclear riboproteins to form a splicing machine called the spliceosome. The animation is showing this happening in real time. The spliceosome then brings the exons on either side of the intron very close together, ready to be cut. One end of the intron is cut and folded back on itself to join and form a loop. The spliceosome then cuts the RNA to release the loop and join the two exons together. The edited RNA and intron are released and the spliceosome disassembles. This process is repeated for every intron in the RNA. Numerous spliceosomes, shown here in purple, assemble along the RNA. Each spliceosome removes one intron, releasing the loop before disassembling. In this example, 3 introns are removed from the RNA to leave the complete instructions for a protein.
Okay. And I do want to say one other thing about the nature of the class, because it relates to this. Yes?
How does it, is there like a sequence of codons that tells it it's an intron, or how does it know?
That is unclear. But yes, there is no question that there is some sequence. It's not as straightforward as a simple stop codon or start codon. But yes, generically, that is what it is. It's a say, cut me site and another cut me site. That's right. And then it involves recognizing those and then bringing the spliceosome to those sites and actually then doing the excision. Okay? Yes?
What happens to the introns after it's spliced out?
Good question. Mostly they're degraded. I don't know if they have another role. I don't know. Okay, let me, once again, talk about what happened like in the last lecture. Some people in your comments were sort of upset that, I don't have the answers, and we're wasting all of our time. And I understand that point of view, especially if you view this as, I'm up here, I'm getting paid a lot of money. Wish it was more. To impart to you a certain wisdom, a certain knowledge. And there is a certain amount of that goes on. But in truth, what happens is at the end of the day, that is at the end of the course or 6 months later, you're going to forget a lot of the information that I've given you. What I hope that you will take out of it is a certain way of thinking. So when somebody asks a question and like, I don't know, that's a real opportunity for me to go back and learn. And it's an opportunity as well for you. And so if you care to go look it up, write a little section, you'll teach me, I'll then teach the class. And if you do that section, I will write it down in a grade book, and at the end of the term, I will give you some sort of credit for it. But it's a real opportunity for you to learn. And in fact, that's one of the great things about research, is you come in with a problem and you have no idea how to solve it. And the first question you need to ask is, what are the questions that I need to be asking? And then you go look it up, or you have to. That's the process that really matters. Okay. Okay, so on to X-ray diffraction, and in particular, we're going to do the X-ray diffraction of a piece of DNA, and the thing we want to figure out is the major and minor grooves, the interspacing distance, and what the periodicity is. And the fundamental task is to go from the diffraction pattern, which is something like this, to the actual DNA structure. And the thing you notice, and we went over this last time, is there's obviously an X pattern. So what does that mean? Why is there an X pattern? Why isn't there, a Y pattern or a Z pattern? And what about the angles between them? And the fact that there are lines, 1, 2, 3, 4, 1, 2, 3, 4, 5, etc. And there are 10 of them. What does that mean? And in particular, the fourth line is evidently missing. And why is that? And lastly, that there is a diamond type of pattern. Okay, so what we need to do is go over a little bit of the basics of diffraction patterns. And so you have a wavelength coming in that tends to be X-rays, and in fact, we'll go and understand why they're X-rays. They have a certain amplitude and a certain phase, and if you have two of them, they interfere with each other. And you have either constructive interference, in which case you get something that a lot of light there, or you get destructive interference, where in this case the waves are out of phase by lambda over 2, and you get complete interference. So if delta L, the difference in length between the two, is equal to lambda, they add. And if delta L is equal to 2 lambda, they also add. So you get constructive interference, a series of them, where delta L, the difference is equal to n, where n is an integer, times lambda, where L is 0, 1, 2, 3, etc. Okay? If the two diffracting atoms are a half a wavelength apart, you get destructive interference. You also get destructive interference if their delta L is 3 times lambda over 2. And essentially, you can continue this pattern. And so the destructive interference occurs when 2 times, we call it n prime plus 1 divided by 2 times lambda, where n prime is 0, 1, or 2. Yeah?
So when they say change in L, do they mean like change in length between two wave crests of each wave, or is it just, I'm not sure what change in L is referring to. Is it referring to individual or multiple?
Okay, let's say, actually, you'll see in a second.
Okay.
Yeah.
I just think that change in L is the difference in starting point for the two sources. Like the distance between them. And you just measure them in wavelengths, so it's easy to know if they're canceling out or not.
Okay. So we have a constructive and a destructive pattern. Okay, now what we're going to do is, okay, this is, if you're looking right over here, let's say you have a scatter which looks over there at some angle. Then let's do the simple mathematics. And what happens if you have an interference pattern? So first, you have one speaker. Then if you have a second speaker, and this distance is about L apart, you'll get constructive and destructive interference. So what do you have over here, and what do you have over here? Who can tell me? So at some point, the distance between here and the distance between here is an even number of the wavelengths, or even number of the distance between them. And another case, it's equal to n plus 1 over 2. Yes?
So wouldn't it be constructive wherever the distance is the same and destructive elsewhere?
Exactly. Take a minute, because everybody isn't going like that, and within yourself, go and convince yourself that the difference here and the difference here is a matter of they're even or n plus 1 over 2. Go ahead, you have a minute or two.
So it's going to be the same part. I think it's like the broader gap. Convincing one.
Okay. Why don't the three of you? Can you? Hey, excuse me. Yeah.
Oh, sorry.
Yeah. Why don't you talk and? Good. Why don't the three of you talk? Why don't you introduce yourself? What's that?
What
You-
wave may I use?
Okay. Okay, so you can answer the question? Well, go talk. Where are you going to get constructive interference and where are you going to get destructive interference?
Solid line indicates the wavelength between two solid particles.
Yeah, the solid line, when it is indicating a constructive interference between the speaker and this speaker. So at some point, if the distance is the same between the two, they will constructively interfere. If then the distance is a little bit poor, that is, the distance between this and the distance between this is exactly half a wavelength different, they'll destructively interfere. Is it clear? No. Clear-ish. Okay. So apparently, to some it is clear, and others it isn't. And some, for those of you who isn't, apparently there's a stalemate going on. Go ahead. Tell me. What's a stalemate?
I'm pretty sure I'm wrong.
You're pretty sure? Well, gee.
Those are the guys that sort of sure.
Okay. So, yeah, that's you.
Where the interference patterns like match up, that would be the constructive interference, and like where there's the gap, that's the destructive.
Okay, so, go ahead.
Space would be destructive, but then when they line up, it's constructive.
Okay, so this is like destructive and this is like constructive. Yes?
Yeah. Wait. No,
I don't, like,
Yes.
I mean, it all depends what we represent the waves as. So, like the blank spots, are they crests or troughs?
Well, what do you think? If you can do this experiment, these two speakers are there, and they're going like this, and you put your ear right here, and then you put your ear right here. Is there a difference that? Will you hear a difference? Okay, so
yeah.
for sure, you will hear a difference. Will it be loud or soft here? Loud or soft there. That's the constructive versus destructive interference. So this is assuming that this is going at a certain frequency that you can hear, let's say, at 5,000 hertz, 5,000 times per second. This one is, and this one is. And you can see clearly if there's a point right over here, right, where the distance from here is the same as the distance from there, then what happens? Constructive interference. Yeah? So, okay. Now, if you can also get constructive interference at another point, happens to be over there. And you can get constructive interference at another point, where here the delta L is equal to 0. That is, the path length difference is exactly 0. Where here the path length difference is L. So constructive interference and destructive interference. And in fact, that's exactly what you see. This is two water waves. The same thing is applying to X-ray diffraction, just at a much, much smaller scale. Plus, there's some difficulties which we'll get to at the end about this. Okay? And in fact, it's neat. You can change the distance, the L, and therefore where you're getting the destructive and constructive interference is going to change. And now let's do a little bit of the math. Comes in, it scatters. This is just for 1. Here you have it scattering again, and you get interference. So what we have is we have a plane wave coming in. You can represent this as a series of guys all emitting. There you get one. There you get the other. And you get constructive interference. This is now, instead of sound, it's light. It'll be light there. And you'll also get destructive interference. Oh. And oh. Oh. Okay, let's get the mathematical formula. I think we'll do it on this one. So let's say there's a distance p between them. Will come in. These constructive interference, yes. It's a bright spot. Now, we're going to show what it is at some wavelength, not wavelength, at some angle theta. Delta L is lambda over 2. So that is going to be destructive interference. So where delta L is equal to p times sine of theta. So we're going to get destructive interference when delta L is equal to n plus 1 over 2 times lambda, or it's p sine theta. And similarly, we're going to get constructive interference, bright spots, when p sine theta, which is delta L, is equal to n times lambda. So what we're going to see is at theta equal to 0, you're going to get constructive interference. When theta is equal to the arc sine of lambda over 2, that is, so we take the arc sine of both of those, get the arc sine of lambda over 2, you get another constructive interference. And then when the arc sine of 2 lambda over p, you get constructive interference again. Okay? Okay, let me ask you a question about X-ray diffraction. In a sodium chloride crystal, you have sodium, then chlorine, then sodium. The distance between the atoms is 0.282 nanometers. Which of the following wavelengths could be used to see a clear diffraction pattern? Your choices are 0.1 nanometers, 1 nanometer, or 10 nanometers. Go ahead. You have a minute and a half to discuss. So explain to me what the answer is and why.
Did he mean like did he only mean to But here's the thing, like, figure this out mathematically. I feel like it has something to do with in the P side. But how do we?
I want to know mathematically what it is.
This is the situation for you when you get diffraction.
So will you follow the different wavelengths? Like data gets so big that it's probably
Okay, who is the answer? So you've answered. Come on, you've answered. Yes.
Yes, according to this sign equation, if the lambda is like larger than the distance, and you will not find any theta to match it because the largest quantity is 1. So.
Good. So this lambda over p
Should be smaller than 1.
in order to get some sort of constructive interference. So if lambda over p is what? Is less than 1, you get constructive interference. So that means lambda is less than p. And p is 0.28 nanometers. So what's the answer?
0.1.
A. Okay, quickly.
Yeah, so in this situation, all we're looking for is just a small enough data for us to see the interference pattern.
Yeah.
Okay.
Okay? So that, in this case, if you're going to do an X-ray diffraction pattern of sodium chloride, you better use an awfully short wavelength. Okay. So here, this is getting P again. There you get constructive interference. There again, you get constructive interference. And there again, you get constructive interference. So you get constructive, and then you get constructive, you get constructive. This should be reminding you of you're going to get, we haven't figured out the x, but here a certain periodicity goes along with the periodicity of the DNA. In fact, actually, this is kind of interesting. What if P is large? What happens to theta? That is, the theta gets smaller or gets larger? So P gets bigger, theta gets smaller. That's a really important thing to just generically know, that there's an inverse relationship between the periodicity that you actually have and the diffraction angles, the distance between the constructive interference or the destructive interference. They're inversely related. Okay. Okay. So now we had just a 1D situation. Now, what happens if we have 2D? So for a simple array of something like this, what does the diffraction pattern look like? Of this, and then of this, that is the distance P is decreasing, and then also it has to do with the orientation. Okay, so you have to work this out. So what do you think is going to be the diffraction pattern in A? Go ahead, go work it out.
Which way is it traveling? To the left, to the right, up, down? Everything that's horizontal is going to either be stopped by a solid piece or just go same thing vertically except for sort of.
Is the light coming from in front of the screen, or is it coming from like the side?
That's what I thought. That's what I thought.
One question is, which direction is the light coming from? And it's coming from out of the page. And
oh.
Oh.
I remember it has a inverse relationship too, like that one.
like for aliens, gave them like going first, but you can see it and then you can start to go. Other one means you kind of go like
John? Okay. So what's for A? Yes, Katie.
It would be like horizontal, like and since they're further apart, then compared to B, it would have a smaller theta compared to B, which would also be horizontal bars, and then
Horizontal bars. Horizontal bars. So you say, yeah, and you say, no.
They can't be horizontal bars because the slits are horizontal, so all the light will be coming through the slit and not interfere horizontally, but instead vertically as the light fans out up and down.
Say that again more slowly and
Okay.
turn around.
So the slits are horizontal, so all the light passing through the horizontal lines won't interfere with each other because it's not diffracting horizontally. Instead, as the light passes through the slit and fans out up and down, that's what will interfere with each other, so you'll get vertical diffraction patterns.
Something like that. Okay, I'll let you think about this. And okay, let's assume that this is the situation in A. Now what it is in B. The difference between the diffraction, the constructive interference or the destructive interference, however you want to put it, is it going to get bigger or smaller? Why is it getting bigger? Your P is decreasing, remember, with this? So it looks like that. Okay, now we turn it on its side. Turn this on its side, and right, this should 90-degree turn, therefore this is a 90-degree turn. Whoop. And C, and then D. Okay, so I want you to go home and actually think about it, and I'm also going to give you an article which has this. Okay, yes?
Were they actual dots, or did you just make them simple? Would they be lying?
Oh, I thought it was like the constructive interference.
yeah.
Dots.
Wouldn't it be like bright spots and then everything in the middle would be kind of like dimmer or whatever? Like until and then if you get right in the between the lines, it'd be like full destructive interference or whatever.
Okay, if you want,
There'd be like a periodicity.
yeah, there is a periodicity. Okay. Okay, so notice the inverse relationship between spacing in the array and spacing in the diffraction pattern. It turns out that mathematically, if you want to do this more rigorously, it's called, one is the Fourier transform of each other. This is not required for the course, but how many people have taken Fourier transforms in some whatever math or physics or, oh, well, that's actually good for me to know, because later on, actually, I'll talk about Fourier transforms, and you guys will know what I'm talking about. Okay, but for now, we're not going to deal with it. Okay, now, what about if you have, remember what we just did. We have two-dimensional space by D, and then let's say we have the same thing, but it's moved this way. What will the diffraction pattern look like? In this case, we had a certain diffraction pattern, like this or like this. And then what is the diffraction pattern going to look like when we've just rotated it? It's like a zigzag. Let's say you have this, and you have this, and you have this. So it's just like the two dimensions that we had, but they're turned. That is, you have the periodicity. And this guy is going to produce a diffraction pattern like this. And this guy is also periodic, but it's tilted. So the fact that it's tilted means that you're going to get another diffraction pattern that looks like this. Ah, what do you know? We see an X pattern. Some people are smiling, yes. And notice that the angle is going to have to do with something. Helix, that's good. Okay, so now let's take another situation. Normal DNA, you have the X, you have the angle between them, and you also have another, call it alpha, another angle, which corresponds to the distance here. That's, let's say, the normal DNA. And now let's say you have a new form of the DNA, where the angle between the spots are the same, but this angle is somewhat less. Which statement regarding the new DNA structure must be true? A, it cannot be a helix. The helix repeat distance, P, must be different. It must be a wider molecule. So is P going to relate to this or to this? You have 2 minutes to work on it. After this, we'll take a little bit of a break because I'm reminding myself you for sure deserve it. Okay, so go for it. Do you know? Okay, you're.
Deep data's the same amount, right?
Yeah, this is the same.
No, because he was different and more or less the same. It was a wider
Do you have an idea? You what? Yeah, go ahead. So,
I think distance P must be different. Because when you show the pictures, something like this would give us that. But if the alpha, this changes, then I think it's not A. I'm not sure.
so how does the helix repeat? P. How is that related to theta or to alpha? You have two parameters. You have theta and you have alpha. P is the periodicity. So is P related to theta or is it related to alpha?
From what I said, it's alpha, but I'm pretty sure the previous
Okay. Okay. So the question really is P, the periodicity, related to this angle, or is it related to the distance between the spots? It's related to the distance, you're saying, between the spots. So here is the distance between the spots. Is that the same? Yes. Therefore, you know the periodicity must be the same. Okay. What do we know about these things in terms of whether they're helix or not? They are. Why are they a helix? Because it's the X. That's okay. So now the only thing is alpha, the angle between them. Yeah? Okay. So alpha, the periodicity must be the same, although alpha must be changed. And that is, this guy, the only way to get alpha to change is to widen the original structure. Okay? So the answer is, it must be a wider molecule. Yeah, but whoa, you guys are cutting into your stretch time. Okay.
Oh, well, we can do the stretch first if you want. I was going to ask, I don't exactly understand why the helix makes an X pattern, but you can answer that after the break if you
Okay, that,
Sorry, everybody.
that, okay, the reason is because these are at some angle over here, and so the diffraction pattern is going to be like this, essentially always perpendicular to that line. So if you have this, so you have one line, then now if you have structure that looks like this, it's going to look the pattern like that. So if you have two of these, that is, you know, yeah, whoop. This is just this plus this, and that will give you the diffraction pattern. Okay, yes?
I have a quick question. Which way is the light coming from? Is it coming from the left or the right or like into the board?
Out of the screen.
Or into, either one. Okay, so we should take a break. I'll give you a minute and a half. Okay, everybody stand up and stretch a little bit. Stand up, go ahead. No, okay. Yes.
So for the previous problem with the X-ray diffraction pattern, wasn't change in P the same for both instances? Or was one larger than the other? Because if you look at the presentation, it kind of looks the same.
Yeah. What? P is related to this distance.
Yeah.
And lambda is the same, so therefore P must be the same.
So change in theta, therefore P1.
There is no change in theta.
So both delta theta values are the same.
Yes, absolutely.
And so therefore P values are also the same.
That's right.
So what is inducing this to be a wider molecule if P is the same?
Okay, so clearly alpha is different. Okay, so P is the same here and here.
But it's not the same widthwise. You know what I'm saying?
Well, the difference. Remember, if you turn the thing that in real space, it looks like, you know, this, and therefore the diffraction pattern will look like this. And so if it is like here, the diffraction pattern looks like this. Okay. What? I will answer it again after class if you can stay. Okay. Real quick.
So how do you know that like you're shooting it through one strand and it's not like folded up and hitting another strand and that's
Well, okay, if I could have. So the question is, I think, how do we know that, in fact, we have, you know, that it looks like this as opposed to, you know, at all different orientations. That is, in fact, the whole thing, that you have to prepare the DNA such that you are looking at an ensemble which is all identical. Because if you have a helix that, you know, is here, and another helix that is here, another helix that are there, you get a mishmash. You get no diffraction pattern at all. The whole trick was to prepare the DNA in a reasonably well-ordered fashion. In fact, that's what Rosalind Frank, who did not win the Nobel Prize, which is sort of outrageous, she did.
She did not win because she passed away, though. But it's so good, like,
That's what they say, but you don't think
actually, she did pass away. She died really young of cancer. I think she was like 46 or something. And I think that was, in fact, before the Nobel Prize was awarded. And in fact, they don't award any prizes post-mortem. Yes. No. Okay, so we have to get rid of the whole thing. Okay, so first we have an X pattern. So that means we have a helix. The layer lines, remember, smaller means P is bigger. So we can see the layer lines. So given that, you know, we can know the theta and we know lambda, therefore we know the periodicity. We also know how strong of a helix it is by the angle, what we're calling alpha. Okay. We know this, we know this, and we know the fact that it's a helix. Okay, so that's the fact that there are 10 layer lines implies that there's an interbase spacing of P over 10. And finally, we have a problem that the fourth layer line is missing. Here, in this case, the black corresponds to constructive interference. And so apparently at the fourth layer line, it's somehow destructively interfering. And we need to be able to solve that. But it's important that we've been able to figure out the DNA. Now, we've gotten the 3 parameters. It's a helix with a certain periodicity, and there's a smaller periodicity which corresponds to the distance, in this case, between the bases. And now we have to understand the missing layer lines. And the missing layer lines is just an extension of what we've done. And that is, This is this is destructive interference, just previously what we've done. So we get this, get constructive interference. This is all what we've done. Now, somehow we must get some additional interference effect, some sort of destructive interference. So imagine that you have a periodicity P, and let's say that you have another periodicity which also is P, but they're slightly offset from each other. Remember what we were doing yesterday? Or you know, if you have two strands, they're identical to each other in phase, you don't get destructive interference. But in fact, if one is slightly offset from the other, then you have a major and minor groove. And in fact, that's what is going to happen. And so here you have so-called, this is the minor groove, and this is the major groove. Okay, so what will happen here? So you get, so this is n lambda over p, which is constructive. It may be out of phase with the light that is diffracting from this one. The out of the destructive is 2n plus 1 over 2 times lambda over q, and you'll have to work that out. And so q is equal to 2n plus n prime plus 1 over 2 times p over n. Again, you'll have to work this out. And for the fourth layer line, n equals 4, or n prime. So, n is equal to the fourth layer line. So q is equal to 2n prime plus 1 over 8 times p over 2 times 4. Or p is equal to 1/8. A q is 1/8 of p, or 3/8 of p. So at that point, you will get destructive interference. Now, you have 1/8 or 3/8 of p. What? So what's happening? Turns out that 3/8 times p, that's a reasonably large distance, such that you can actually resolve it. You can see it. This is 1/8 of p, so that's 0.125 p. It's essentially, it's too small, that they didn't have the resolution for that. Okay. Yes?
Where did the p over n term come from? Like, can you explain that again?
Sure. So sine of theta is n lambda over p. That's where you have this, okay? And you want to pick a point at some angle theta where this is going to be out of phase. So the out of phase condition is equal to this. So you have this equal this. So n lambda over p is equal to this. So p over n is equal to this. Yes?
Where's n prime coming from? I get what n is, but what's n prime?
N prime is or you tell me. Where is n coming from?
N is the layer that we're looking at, isn't it? Since it's 4. The fourth layer is the one that's being destructed, so that's why n equals 4.
Yeah, but this is in general for anything. So n prime is for, again, it can be anything. So we actually, n equals 4. And so then the question is, will there be some n prime that you'll get it such that there's complete destructive interference between this line and this line? And so you just imagine, so you say, well, will n prime equal to 0? Well, that's 1/8 p. What about n prime equal to 1? Well, n prime, that's 3/8 p. And what about n prime equal to 2? That's 5/8 p. What about that? That actually will be on homework. Why isn't, or is it, that which contributes? Okay. We haven't gotten to quite the end of the electron diffraction. Next time we'll have just some more realistic modern day equivalent, but there will be homework which will involve reading in terms of why we're different than worms, and it will involve reading in terms of essentially where this lecture came from. There's a journal of, I don't know, physics education